Assalamualaikum and good evening to Dr. Abdul Halim Abdul Latif. I am Amirah Syazwani binti Saiful Bahri, and today I will present the assignment of paper review based on literature review and past research of my title, which is Spectral Decomposition. In this presentation, I have referred mostly to a journal regarding predictive deconvolution in seismic data processing in Atala Rivers, Nigeria. I also use some other journal to add the information regarding spectral decomposition. So the contents for today's presentation, I will start with abstract, introduction, then followed with problem statement. Then I will present the location. The location is based on the one of the journal that I have used the most for this presentation. Then I will present the literature review, analysis, field data examples and discussion, and lastly the conclusion and reference. Now I will start with abstract. Predictive deconvolution is the use of information from the early part of seismic trace to predict and deconvolve the later part of that trace. It is an attempt to attenuate multiples which involve the surface or near surface reflectors. During the processing procedure, the information collected in the field is transformed into a format that greatly facilitates geological interpretation. The prediction filter was created to produce the predictable component of a seismic trace, while the remaining unpredictable part, the error series, is essentially the reflection series. The design shaping filter is used to convert the recording signature to its minimum phase equipment and apply it to the input record. Figure shows A input length seismic data, while B is the data after frequency domain predictive deconvolution is applied. Now I will present the introduction. Basic objective of seismic processing is firstly to convert the information recorded in the field into a form that most greatly facilitates geological interpretation. Secondly, it is to eliminate or at least suppress all noise in form of reverberation and multiples. The importance of predictive deconvolution includes applied to improve temporal resolution by reflex shaping and removal of short period reverberation. The primary reflection coefficients are assumed to be an unrelated random sequence in this method. It is assumed that the primary reflection and multiples are orthogonal to each other. Now I will present about the other researchers' perspective regarding spectral decomposition. There are many researchers that identify predictive deconvolution according to their research. Firstly is Milton and Bjorn, 2007. They stated that, in general, the Levinson principle can be used to recursively solve linear equation. It can also be used to directly update error terms. Wang, 2006, stated that the Wiener prediction filter is effective for the reverberation when the data are stationary. Secondly, he said that results of using the Wiener prediction filter, adaptive predictive deconvolution on non-stationary data show that the adaptive method is far more effective at removing multiples. By Zhang et al. 2009, the move out of multiple is changeable in tracegather, and to remove multiples in entire tracegather, the predictive length must take far traces into account. Secondly, predictive deconvolution to remove multiplies is not as effective as other methods of improving resolution. Because it may increase fake energy after processing, the length of the predictive operator must be greater than the period of multiple. Based on Robinson 2006, he stated that transmission energy spectrum is the difference of input energy spectrum and the reflection energy spectrum. Hence, from the computed energy spectrum of the transmitted wave, we can compute the prediction error operator that contracts the transmitted wave to a spike. Based on Maghrib and Lamourex 2010, they stated that non-stationary predictive deconvolution compares reasonably well to Gabor-Decon when the prediction distance is in unity. Not quite as good as Gabor-Decon is attributed to the fact that the deconvolution operators are designed independently rather than simultaneously. Tanner, 1980, said that predictive deconvolution is the tau p domain as a remedy for the first effect. And lastly, based on Paris and Handy 2000, they said that similar ideas with Tenor 1980 have been tested, such as predictive deconvolution in the radical trace domain. Now I will present the problem statement. Predictive deconvolution is an integral part of seismic data processing, aimed at compressing the seismic wavelet, thereby increasing temporal resolution. Certain assumptions are made in predictive deconvolution during the processing process. Firstly, the Earth is made up of horizontal layers of constant velocity, and compressional plane waves that impinge on layer boundaries at normal incidence are generated at source. In this case, no shear waves are generated. Secondly, the waveform source does not change as it travels in the subsurface. This means that it is stationary. Thirdly, the noise component in NT is zero. Next, reflectivity is a random process, meaning the seismogram has seismic wavelet characteristic. And lastly, the assumption is the seismic wavelet is minimum phase since it has a minimum phase inverse. So now I will present about the location of research based on a journal of from Iqbal JETAL 2012 about spectral decomposition analysis at Atala Rivers, Nigeria. The Trans-Atala 3D prospect, where the data were obtained, spans a large area of OMLS, or mission lines, which are 35 and 46. Total prospect surface area is approximately 256 km square. The area is swampy and low-lying with surface elevation gradually rising from 2.28 meter in the south to 1.98 meter up north. The prospect covers Burik Bin and Okbotobo fields. The adjoining communities are Ikuruk Bin, Basan, Lobia, and so on. These are all in Western Ijaw local government area of Rivers State. Now I will start to present about the analysis of spectral decomposition based on Iqbal J. EPAL journal. Assuming xt is the desired input and t plus y is the predicted value at some future time, where y is the prediction lag, it can be shown that the filter used to estimate xt plus y can be computed by using a special form of the matrix equation shown in equation 1. As the desired output xt plus y is the time advanced version of the input xt, we need to specialize the right side of the equation for prediction problem. If we consider a 5-point input time series X, where I equals to 0, 1, 2, 3, 4, and Y equals to 2, the autocorrelation of X1 of Xi is computed as shown in table 1 below. The cross correlation between the desired output X t plus 2 and the input Xt is shown in table 2 below. Comparing tables 1 and 2 and noting that Gi equals to Ri plus Y, which R equals to 2 and I equals to 0, 1, 2, 3, 4. Equation 1 could be rewritten as shown below. The prediction filter coefficients AI, where I equals to 0, 1, 2, 3, 4, could be computed from equation 2. The actual output could be computed as shown in the table 3. As we are trying to predict the time advanced form of input, the actual output is an estimate of the series xi plus y, where y equals to 2. The prediction error series is shown in the table 4. The results of table 4 shows that error series could be obtained directly by convolving the input series with a filter with coefficient 1, 0, minus A0, negative A1, negative A2, negative A3, negative A4, as shown in table 5. The results of table 4 and 5 are identical for beta 2, beta 3, beta 4, beta 5, and beta 6. The series A0 to A4 is known as prediction filter, and the series 1, 0, negative A0 to negative A4 is called the prediction error filter. Applying this on the input series, the filter yields the error series in the prediction process. The prediction filter yields the predictable component of a seismic trace, while the remaining unpredictable part, the error series, is essentially the reflection series. Equation 2 can be generalized for the case of an n-long prediction filter, n and y-long prediction lag as shown in equation 3. The design of the prediction filters require only autocorrelation of the input series. There are two approaches to predictive deconvolution. The design may be carried out using equation 3 and applied on input series as shown in figure 1. An alternative is to design and convolve the input series, the prediction area filter as shown in figure 2. The slide is now showing the figure 1 and figure 2. Figure 1 is a flowchart for predictive deconvolution using predictive filters, while figure 2 is a flowchart for predictive deconvolution using prediction error. Figure 3 now is showing a flowchart for interrelations between various deconvolution filters. It shows that it can be used to solve a wide range of problems and that predictive deconvolution is an integral part of seismic data processing aimed at compressing the seismic wavelet, thereby increasing temporal resolution. Now I will present the field data examples and discussion. Field data examples are now used to examine the deconvolution parameters. Figure 4 shows a CMP, common midpoint gather, that contains 5 reflections at around 1.1, 1.35, 1.85, 2.15 and 3.05 seconds. There exists reverberations associated with these reflections. In figure 4 through 7 and figure 8, the input CMP gather was 6 seconds long, but only the first 4 seconds are displayed. The analysis of the time gate to estimate the autocorrelation function will begin with examination of the deconvolution parameters. Figure 4 shows autocorrelation window test used to design the deconvolution operator. Solid bars indicate the window boundaries. The entire 6-second length was included in A. The autocorrelograms are displayed beneath the records. Now figure 5 is showing the test of operator length. Figure 5a shows input gather deconvolution using prediction lag, which equals to 4 milliseconds for spiking deconvolution, 0.1% pre-whitening, and prediction filter operator lengths. B is 40 milliseconds, C is 80 milliseconds, D is 160 milliseconds, and E is 240 milliseconds. This short 40 millisecond operator leaves some residual energy corresponding to the basic wavelet and a reverberating wave train in the record. For a 60 millisecond operator, no remnant of the energy is associated with the basic wavelet and the reverberations. Operator longer than 60 milliseconds does not change the result significantly. The effect of prediction lag is examined in figure 6, shown in the slide. 160 millisecond operator length and 0.1% pre-whitening are fixed while prediction lag is varied. An increase in the prediction lag will result in the deconvolution process, which makes it less effective in broadening the spectrum. In the extreme, the deconvolution process is ineffective for a 100 to 8 millisecond prediction lag. The test of percent pre-whitening is shown in figure 7. The corresponding autocorrelation is beneath each record. The window used in autocorrelation estimation is shown in figure 4. By the deconvolution process, it becomes less effective and the percent pre-whitening is increased. Deconvolution using prediction filter operator length of 160 milliseconds. Finally, figure 8 is showing the signature processing. A shaping filter is designed to convert the recording signature to its minimum phase equivalent and apply it to the input record A. The output B then has been processed by predictive deconvolution using operator length of 160 milliseconds and prediction lag C shows 4 millisecond spike deconvolution, while D and E are 12 milliseconds and 32 milliseconds respectively. Lastly, I will present the conclusion for my presentation. Predictive deconvolution is the process of predicting systematic noise such as reverberation and multiples using information from the earlier part of the seismic trace. It is an attempt to attenuate multiples that involve surface or near-surface reflectors. The design of the prediction filters, which require only autocorrelation of the input series, is involved in predictive deconvolution. The output was processed for this research with an operation length of 160 milliseconds and prediction lengths. For reference, I have used 5 journal, but the main journal that I have used is from Ekbai JETAL 2012, entitled Predictive Deconvolution in Seismic Data Processing in Atala Prospect of Rivers State, Nigeria. So that's all for my presentation. Thank you to Sir for your attention and all the teachings for throughout this semester.